Hello, and welcome to your first lesson in Unit 6, where we're going to be talking about solubility, solutions, solubility, equilibrium. So first of all, we need to kind of review the concept of a solution. So a solution is a homogeneous mixture of two or more substances. So homogeneous means that it is the same throughout. This is in contrast to a heterogeneous mixture, which is going to be different throughout. So heterogeneous mixture, think of like sand. A homogeneous mixture, you can think of like coffee, sweet tea, vanilla ice cream. It's going to be the same throughout the whole sample. And a solution is going to be different than its components. So water and salt are very different than salt water. So the solvent is the thing doing the dissolving. Water is obviously our most common solvent, but not the only one. And then the solute is the thing being dissolved. So there are many types of solutions. The most common and the one that always comes to mind for us is a solid within a liquid, right? So salt water. But that's not the only type of solution. The atmosphere is a solution, a homogeneous mix of gases. Ethanol being dissolved in water or isopropyl alcohol being dissolved in water is a liquid solution, so like rubbing alcohol. A solid can be dissolved. The word sounds weird in this context, but a solid can be dissolved in a solid, so an alloy. So brass, for example, is a mixture of zinc and copper. A gas can be dissolved in a liquid, dissolved oxygen. All the fishies and aquatic species are very thankful for dissolved oxygen, carbon dioxide in your soda. And then, of course, a solid in a liquid, which is the common one we think of when we think of a solution. So in order to form a solution, we have to break two different interactions. We've got to put energy in to do that. And then we form a new interaction which releases energy. In our next unit, we're going to focus all on that, like on thermochemistry and on the heat of reaction. So it's not super important that we focus on it now, but I do want you to understand the process involved in creating a solution. So we've got to take apart or break down the interactions between the solute molecules. We got to break apart the interactions between the solvent molecules, and then in mixing them together, we create new interactions between the solute and the solvent. And depending on how much energy is needed to break the interactions and how much energy is released when the new interactions form, can make the dissolution process endo or exothermic. So the formation of a solution is something that we call spontaneous. Again, we're going to talk all about that next unit. But what it means is it doesn't require added energy. So if you put a soluble salt into water, it's going to dissolve, even if you just let it sit there and do nothing. If you stir it, it'll dissolve faster, but it will dissolve. It's a spontaneous process. It decreases its internal energy, so it's an exothermic process, and it increases disorder, which is entropy. Again, we're going to focus all on that next unit, so not super important right now. So this is just showing how, depending on the magnitude of the energy required to break down the solute, and solvent, and then how much is released. If how much is released is greater, then it's going to be exothermic. And if how much is released is less, it's going to be endothermic. So the term solubility is the maximum concentration that can be achieved under given conditions. So we can think about it like this. Let's say we have a solid, let's do silver chloride. So that just dissolves into silver ions and chlorine ions, okay? We're going to learn in just a minute that it is in equilibrium, okay? So the solubility is the maximum amount of ions that can be produced. So if we set this up like an ice chart, what we realize is that solubility is our X in an ice chart. So this whole time we've been doing equilibrium and we solve for X. That's going to be, for a solid dissolving, X has a name of solubility, the molar solubility. And the solubility of something depends on temperature and a couple other things. So we have three terms for basically at what point a solution is in. Is it before it's reached its solubility? Is it at its solubility? Or is it over its solubility? So if it's right at its solubility, if it's at its maximum amount, we call it a saturated solution. So if you are told that something is a saturated solution, that means that the maximum amount of dissolving has happened. The maximum concentration of ions is present. If it's unsaturated, it is not to its saturation point yet. So there's less than its maximum solubility. And then if it's super saturated, then it actually has a greater amount in there than its solubility allows, which seems not possible, right? Because if our solubilities are maximum, how do we dissolve more than our maximum? And that requires changing some condition in order to achieve that. So for example, if you have ever made super sweet tea, you don't put the sugar in it when it's cold, because very little sugar dissolves in water when it's cold. But lots of sugar dissolves when it's hot. So we heat it up, we dump in the sugar, and then we slowly cool it down. And so at the temperature that you drink the sweet tea, ice cold, there's way more sugar in there than would have been in there if you had tried to dissolve it while it was cold. Another example is we put super high pressure in soda cans to dissolve way more carbon dioxide than we could at normal atmospheric pressure, which is why when you crack it, you hear that sound of all that pressure releasing, because that much, and then you see all the the little carbon dioxide bubbles coming out, because all of that carbon dioxide, once you open that and it's now at atmospheric pressure, is way super saturated. So some factors that affect solubility is just the structure and identity of the solute and the solvent. We have a little thing we remember: like dissolves like. So a polar thing is going to dissolve another polar thing. So that's why ionic compounds dissolve so well in water. Non-polar things only dissolve non-polar solutes. Pressure is exactly what I mentioned, like with the soda can. So pressure only affects the solubility of gases, because gases are the only, solids and liquids are not affected by pressure, so only gases. If we up the pressure, we're going to up the solubility. Again, that's why we do these highly pressurized, shoving that carbon dioxide into soda cans, and then when you open it, it all gets released. Temperature is another thing. So for solids, temperature typically increases the solubility. Not always. You can see there's this example of cesium sulfate where it actually decreases. And you'll notice for sodium chloride, there's barely an increase in solubility with temperature. But for the rest of the salts that are shown on this graph, temperature greatly increases their solubilities. But for a gas, it decreases typically with temperature increasing. So that kind of makes sense if we think about what do gas molecules do when they get more and more energy? They move faster. And so they have enough energy to escape whatever they're dissolved in. So a good example of this is thermal pollution. So this is what happens and causes loss of aquatic life, like fish and other populations of aquatic animals and plants, around like power plants. So this increase in temperature in that area causes a decrease in the level of dissolved oxygen, which causes a problem for aquatic life. So just a good real life example. Okay, so there are multiple units for concentration. And why are we talking about concentrations? Well, we're talking about solutions, and solutions have something dissolved in something, so they have a concentration. Obviously, the most common is molarity. That's the one that you are familiar with, moles per liter. But this can change with temperature, like we just said. So sometimes we use something called the mole fraction, which is the moles of something over total moles, or the molality, which is the moles per kilogram. That's not going to change. However, for our purposes on our tests and on the AP exam, we're only going to use molarities and moles per liter. Okay, so now that we've talked about just a refresher on what is a solution, what are the properties, how does it form, what affects it, now we're going to talk about the actual reaction. It's not really a reaction, but the dissolution of the solid. So solids dissolve to form aqueous solutions. So the solid becomes ions. Initially, we're thinking of this like an ice chart, the initial conditions, there's no ions, it's all solid. But over time, we create these ions. Well, as this concentration increases, those ions can bump back into each other to reform the solid, which is the reverse of this reaction. So eventually we reach equilibrium. This is not a new concept to you. This is what we've been talking about for months at this point, right? So the forward reaction happens and the reverse reaction happens. They do not necessarily happen to the same extent, but they're happening at the same rate, right? We're at equilibrium. So in this picture, we're seeing, okay, so we've got a solid down here, and when it reaches equilibrium, then we've got the same rate of solid dissolving as we have the dissolved ones precipitating back out. So that is a saturated solution, and at this point, no more of this solid would dissolve. So when we dissolve a solid in, or anything, into solution, it will reach an equilibrium. So, just like every equilibrium, it has a K value, an equilibrium constant. Since this time we are specifically talking about a solid dissolving, it has its own name, a solubility product constant, KSP. So when we were talking about an acid, Ka. We were talking about a base, it was called Kb. When we were talking about water, it was called Kw. Now we're talking about a solid dissolving, so we call it KSP. But it's still the same thing. It's the equilibrium constant. The thing is, solids do not appear in an equilibrium expression. So when we're talking about a solid dissolving into ions, we only have products that show up in my equilibrium expression, so we do not have a denominator. So for all of your solubility equilibrium expressions, they're not going to have a denominator because we don't put solids in an equilibrium expression. Okay, so here what I'm asking you to do is just write the ionic equation. So what I mean by that is the solid dissolving, and then write the KSP. So for this first one, we have silver acetate. That's going to dissolve into a silver ion and an acetate ion. So KSP is written just like all of our other Ks. Products over reactants, but in this case, our reactants are solids, so they are not included. So products raised to their coefficients. So both of these coefficients are 1, so we just have the concentration of silver ions times the concentration of acetate ions. Simple as that. All right, so now we have to remember to think about how many ions there are. So now we don't just have 1 and 1. So aluminum is a 3+ ion plus 3 hydroxide ions, okay? So for this one, the KSP is the concentration of aluminum ions times the concentration of hydroxide ions cubed. We got to raise it to the coefficient. Obviously, if we're given a name, we got to write the formula first. So calcium is +2, phosphate is -3. So Ca3, PO4, 2. So that is going to dissociate into 3 calcium ions and 2 phosphate ions. So then the KSP is the concentration of calcium cubed times the concentration of phosphate squared. Last one, we've got barium fluoride. It's going to dissociate into a barium and 2 fluorines. So then the KSP is equal to concentration of barium times the concentration of fluorine squared. Okay, I did not just teach you anything new. You knew how to do that. We're just applying it to a solid dissolving now. So it just has a specific name, KSP, and we don't have a denominator because it's a solid. But but nothing we just did was new. Okay, so one thing that's important really quickly now that we've talked about solubility and then the solubility product constant is to differentiate between them, okay? So solubility is the maximum concentration that dissolves at given conditions. It's the position of the equilibrium. It can change. Remember, it's like the X that we solve for. So think about Le Chatelier's principle. So when we had established equilibrium, right, and we had a certain amount of product and reactant, then we added a stress. We had to shift, so the amount of product and reactant changed, but K did not, right? So same thing here. X can be different. Under certain circumstances, under different conditions, the amount that can dissolve can be different. The K, as long as we're at the same temperature, does not change. So the solubility constant is K, so it does not change. It's one singular value, okay? So if you are given molar solubility or solubility, you're given X. You're given, if this is my solid, you are given how much dissolves, okay? So solubility is this X right here. I say minus X because for this one, these are both plus X because it's a 1-to-1 ratio. But if we had, let's say, AgS2, whoops, not AgS2, Ag2S, when it dissolves, sorry, video's in the way, we dissolve into 2 silvers and a sulfur. So for silver, it's going to be plus 2X, and then for sulfur, it's going to be plus X. But there's always going to be 1 in front of your solid because why would we do 2 of them? We're just saying 1 dissolves. So there's always going to be a 1 there. So this will always be minus X. So you know that X is your solubility. Okay. So we kind of have 3 types of calculations that we're going to talk about. We're going to calculate KSP from the solubility. We're going to calculate KSP given the equilibrium concentration or the saturated solution concentration. And then we're going to calculate solubility from K. All right. So this first example, we're calculating K from the solubility. So you're told that copper 1 bromide has a measured solubility of 2 times 10 to the negative 4. So in other words, X equals 2 times 10 to the negative 4. We're asked to calculate K. So here I have written the reaction or the dissolution, and I've written the K. Both of these have coefficients of 1, so it's just concentration of copper times concentration of bromine. So then notice for my ice chart, I only have my products because you could write the reactant if you wanted to, but because it's a solid, we could just X through it. So there's really no point. So initially, I'm going to have no ions. Both of these are 1, so plus X plus X. So then the equilibrium concentration for both of these is X, and from our problem, we know that X equals 2 times 10 to the negative 4. So then I just plug, like always, the equilibrium concentrations into the K value to get my KSP. And I can't read it right now because my face is over it, but you can see it because after I finish recording this, I'll move the little thumbnail. All right, so that's how we calculate K. So here's another example, calculating K from solubility, because this time we don't have 1 ion of each, so it's gonna be a little bit different. So calculate the KSP value for bismuth sulfide, which has a solubility of 1 times 10 to the negative 15. So in other words, X equals 1 times 10 to the negative 15. So here we have our dissolution equation, or dissolving equation. Here we have our K, so bismuth squared times sulfur cubed because of our coefficients. So we initially start with 0. We have plus 2X and plus 3X. So then my equilibrium concentration is 2X and 3X. So I plug in 1 times 10 to the negative 15 to get 2 times 10 to the negative 15 and 3 times 10 to the negative 15. So now that I know my equilibrium concentrations, I plug them into K. So 2 times 10 to the negative 15 squared times 3 times 10 to the negative 15 cubed, and I get a KSP of 1.1 times 10 to the negative 73. So this is an extremely insoluble compound. Okay, so now what I would say do is I would pause and try to do this on your own, and then resume and see if you got it right. All right, so we're given the solubility of calcium fluoride is 2 times 10 to the negative 4. So X equals 2 times 10 to the negative 4. Calculate the solubility constant. So calcium fluoride dissolves into 1 calcium and 2 fluorine ions. So the KSP is the concentration of calcium times the concentration of fluorine squared. So now I have my ice chart. Initially, I have 0 plus X plus 2X. So my equilibrium concentration is X and 2X. Well, I know that X is 2.1 times 10 to the negative 4. So calcium is 2.1 times 10 to the negative 4 at equilibrium. But fluorine is 2 times 2.1 times 10 to the negative 4, which is 4.2 times 10 to the negative 4. So now that I know my 2 equilibrium concentrations, I can plug them into KSP, 2.1 times 10 to the negative 4, times 4.2 times 10 to the negative 4 squared. That is the biggest mistake students make, is forgetting the coefficient is the exponent in your K. So when you multiply this together, we get 3.7 times 10 to the negative 11. Okay, so now this time it's similar, but instead of being told solubility, we're told the saturated solution's concentration. Or, in other words, this is the concentration at equilibrium. So we're given one of these values, and we still have to solve for K. Where this gets tricky is when we don't have a 1-to-1 ratio, and I'll show you what I mean. So cadmium 2 hydroxide, so we have dissolves into a cadmium ion and 2 hydroxide ions. So the KSP is cadmium times hydroxide squared. So initially we start with 0 plus X plus 2X. I'm told that the concentration of hydroxide is 2.4 times 10 to the negative 5. So I put that in here. So remember how we combine these together, that means that 0 plus 2X equals 2.41 times 10 to the negative 5. Sorry, I'm running out of room. So that, to solve for X, I get that X equals 1.21 times 10 to the negative 5. So the molar solubility of cadmium 2 hydroxide is 1.2 times 10 to the negative 5. Because the equilibrium concentration of cadmium is X, then 1.21 times 10 to the negative 5 is the concentration of cadmium. Now that I know my 2 equilibrium concentrations, I plug both of them in. 1.21 times 10 to the negative 5 times 2.41 times 10 to the negative 5 squared, and I get 7 times 10 to the negative 15. So the thing you've got to pay attention to is what ion you're given the concentration for, plug that in, then you got to solve for X to find your other equilibrium concentration. So here's an example. I would pause, try it on your own, and then resume. So we have magnesium hydroxide, which dissolves into magnesium and 2 hydroxides. So the KSP is magnesium concentration times hydroxides concentration squared. I would always write this out so you don't forget that. All right, so then our ice chart, we don't have any to begin with. This is going to be plus X. This is going to be plus 2X. What am I given in my problem? Concentration of magnesium is 3.7 times 10 to the negative 5. So I'm going to plug that in here. So when I combine these, I see that x equals 3.7 times 10 to the negative 5, because 0 plus x equals 3.7 times 10 to the negative 5. So then for hydroxide's equilibrium concentration, I have to do, since it's 2x, I have to do 2 times 3.7 times 10 to the negative 5. So the concentration of hydroxide at equilibrium is 7.4 times 10 to the negative 5. Now I take these values and I plug them in my equilibrium expression. My equilibrium says concentration of hydroxide squared, so do not forget that. So the KSP of magnesium hydroxide is 2 times 10 to the negative 13. All right, so let's do one more like this. So calculate the KSP for iron hydroxide given the concentration of hydroxide in saturated solution is 1.17 times 10 to the negative 5. So that means that's the concentration of hydroxide at equilibrium. So I have FeOH2 dissolves into iron 2 plus and 2 hydroxides. So then my KSP is the concentration of iron times the concentration of hydroxide squared. I start 0, 0 plus x plus 2x. This time we were given the concentration of hydroxide at equilibrium, 1.17 times 10 to the negative 5. So 2x equals 1.7 times 10 to the negative 5. So x equals 5.85 times 10 to the negative 6. So the molar solubility is 5.85 times 10 to the negative 6. Because iron's concentration at equilibrium is x, then iron's concentration is 5.85 times 10 to the negative 6. So K equals 5.85 times 10 to the negative 6 times 1.7 10 to the negative 5 squared. Remember, this was my equilibrium concentration of hydroxide. This is my equilibrium concentration of iron. So the KSP is equal to 801 times 10 to the negative 16. So when we're given the equilibrium concentration, we have to find the equilibrium concentration of the other one and then plug them into KSP. All right, this type of problem, this time we're given KSP and we have to calculate the molar solubility. So it tells me that the KSP for copper 2 iodate is 1.4 times 10 to the negative 7. Calculate its solubility. So in other words, calculate X. So I have my equation here. So K is equal to the concentration of copper times the concentration of iodate squared. My ice chart initially have 0 plus X plus 2X. So I know my equilibrium concentrations are X and 2X. So now I got to plug those in to my K expression. So X times 2X squared is equal to K. Here's where so many people make a mistake, is just this simple algebra. Simplifying this right here. X times 2x squared is not 2x squared, right? We're squaring the whole 2x. So it's 4x squared. So then x times 4x squared is 4x cubed. So 1.47 times 10 to the negative 7 equals 4x cubed. So we got to divide this by 4, and then we got to take the cube root. You can either plug in cube root into your calculator, or this is the same thing as raising it to the 1/3. So taking the cube root is the same thing as the 1/3. If we have to take the 4th root, raise it to the 1/4. The 6th root, raise it to the 1/6. Same thing. And we get that x equals 3.3 times 10 to the negative 3 molar. So that is the molar solubility of copper 2 iodate. All right, so here's an example. We're given the KSP of calcium hydroxide is 8 times 10 to the negative 6. Calculate the molar solubility. So calcium hydroxide dissolves into a calcium ion plus 2 hydroxides. So the KSP equals 8 times 10 to the negative 6. So 0, 0, plus x, plus 2x, x, and 2x. So now I got to plug those in. So I have 8 times 10 to the negative 6 equals x times 2x squared. So that one's going to simplify just like the one on the previous slide, 4x cubed. So then x equals 0.013 molar. That's the molar solubility of calcium hydroxide. All right, one more example, lead to iodide. So we have, and all of these have been like 1 and 2 ions, so they're all going to be kind of the same to solve, but don't get tricked into thinking they're always going to look like that, and you're going to see that in a minute. Okay, lead to iodine, so 1.4 times 10 to the negative 8 is equal to the KSP, which is equal to lead times iodine squared. So 0, 0, plus x, plus 2x, x, and 2x. I'm going to plug those in. And x equals 1.5 times 10 to the negative 30, which is the molar solubility, which is what my question asked me for. If this question asked me what is the concentration of iodine in a saturated solution, I would then take this and plug it in here and do 2 times 1.5 times 10 to the negative 3. So you just got to think about what your question's asking you. But these problems are being solved exactly like all the other equilibrium problems that we've been doing. It's just before we were solving for like hydronium and then we calculated pH from it. Now we're solving for X, but it's called the molar solubility because it is the amount of solid that dissolves. Okay, finally we're going to talk about comparing solubilities of different compounds. If the compounds or the salts dissolve into the same number of ions, so for example, if you look down here, these are both going to dissolve into one, of each. We don't have any coefficients, is another way to put it. If that's the case, we can compare these KSPs directly. So this question is not asking me to compare the solubility product constant. It's asking me to compare the solubility, or X, how much of it dissolves. So to really solve for X, all of these are going to end up being the square root. Because if we do this one, for example, let's do calcium sulfate. What are all of them going to be at equilibrium? Plus x, plus x. So when we set that equal to KSP, we're just going to have x squared equals the KSP. So x is the square root of KSP. So because all of these dissolve into 2 ions, all of them are going to be the square root, so we can just compare them directly. We don't need to find the square root of all of them. That's just an extra step, because the square root of 1.5 times 10 to the negative 16 is still going to be less than the square root of 5 times 10 to the negative 12, which is going to be less than the square root of 6.1 times 10 to the negative 5. So for this one, calcium sulfate is the most soluble, this is the middle, and this is the least soluble. If they dissolve into different number of ions, now we can't just use KSP. Now we have to take that extra step to actually calculate X, because they're not all going to be just the square root. For example, Cu and S dissociate into copper and sulfur. So this is going to be set equal to x squared. And so when you solve, x equals 9.2 times 10 to the negative 23rd. This dissociates into 2 silvers and 1 sulfur. So then where we would set the KSP, when, like, think about it like doing the equilibrium chart, the KSP would end up being set equal to 2x squared times x, which is 4x cubed. When you solve that, you get 3.4 times 10 to the negative 17. And then for this last one, this dissociates into 2 bismuths and 3 sulfurs. So then when we plug in, we're going to have 2x squared, or excuse me, 2x cubed, and 3x squared, because the KSP for this is bismuth squared and sulfur cubed. So then when we simplify this, 2x cubed is 8x cubed, 3x squared is 9x squared. So then that actually ends up being, all right, so, no, I didn't. 9 times 8, 72 x to the 5th. So when you solve for x, you get 1 times 10 to the negative 15. So if we had just used our K values, we would have said that this is the least soluble and this is the most soluble. But in reality, this one's the least soluble and this one is the most soluble. So when you're asked to compare the solubilities, if they dissolve into the same number of ions, just use KSP. If they dissolve into a different number of ions, you have to solve for X. And what we notice, because right now all of them are 0, the initial concentration of the products is 0, and then you're going to have plus whatever coefficient X, and then you're going to plug it into it. We can do this like kind of quickly by just knowing if it's 2 ions, it's x squared. If it's a 2 and a 1, it's 4x cubed, so on and so forth. And as you do more practice, you'll see how I did this faster. If you want to write out the full ice chart, you can. So let's do this for a practice. So we're asked to rank these. These do not dissolve into the same number of ions, so I have to solve for X. So calcium dissolves into 1 calcium and 2 fluorines. So to solve for X, we would get X times 2X squared, right? Because this would be plus X, plus 2X, X, and 2X. So then when I plug those in, I have X times 2X squared. That simplifies to 4X cubed. So then when you solve for X, 2.15 times 10 to the negative 4. All right, this one dissolves into a mercury and 4 chlorines. So we're going to have X and we're going to have 4X to the 4th, which gives me 256X to the 5th. So when we solve for X, so we divide this by 256 and then take the 5th root, we get 8.45 times 10 to the negative 5. This dissolves into 1 lead and 3 iodines, so X times 3X cubed is 27, X to the 4th. We solve for X, we get 4.77 times 10 to the negative 3rd. And then this last one dissolves into 1 and then 2. So we get 4x cubed, 9.01 times 10 to the negative 10. So now when we compare these, the least soluble, it says to do it from most to least, excuse me. So the most soluble is lead, then the calcium goes to the negative 4, then the mercury, and then 10. Whew. All right, I know that's a lot. Sorry it was so long. but we'll do lots of practice and hopefully you'll be good to go.